Hello, everyone. Thank you for joining us today. Welcome to our sixth webinar in our Stream Compensatory Mitigation webinar series. We're so happy you could all be here today. Thank you for participating in this series. My name is Rebecca Kisslinger. I'm a Science and Policy Analyst at the Environmental Law Institute. I direct our wetlands program here. This webinar series is hosted by ELI, and it was developed in coordination with an advisory committee of stream mitigation experts. And we're funded by an EPA Wetland Program Development Grant, and we thank them for their continued support of this work. For those of you new to our series or not familiar with ELI, we're a nonprofit law and policy research organization. We're based in Washington, D.C. Our wetlands program provides timely, balanced information on wetlands law, policies, science, and management through research, education, and convening, such as our webinar series today. We have lots of information on resources on our website, and you can also join our mailing list, Wetlands and Waters from our wetlands page. The URL for our page is eli.org/wetlands-program. We have a really great lineup of planned webinars for this webinar series, and we kicked it off way back in July with a discussion of the status of stream compensatory mitigation. Since then, we've had webinars on assessing stream functions and conditions, restoration approaches, specifically looking at barrier removal, the watershed approach, and monitoring and performance standards. We have a busy spring coming up with webinars on credit debit determination, stream restoration for multiple purposes, and long-term performance of stream restoration projects, and we hope you'll join us for those. We plan to finish up the webinar series in June with a webinar, kind of a wrap-up webinar on the way forward or identifying unmet challenges in stream compensatory mitigation. And we would really love your input on topics for that June webinar. So if you could please, all of you participants, respond to a short evaluation question that will pop up at the end of the webinar. We'd really appreciate your thoughts and input on that webinar. And stay tuned for invites for our upcoming webinars. We'll be sending those over the next couple weeks. And as always, you can find information on upcoming webinars on our website. The URL is here, as well as the URL for today's webinar, where we've posted the presentations, and the archived recording will go there as well. If you have any questions or any ideas, please feel free to email me. My email address is here on the screen. So we're really very excited for today's webinar on defining and using reference. As you all know, the definition of reference is one of the fundamental issues to address in the development of any functional assessment methodology, and is also important for designing projects and evaluating performance. And today we have three really excellent panelists to talk about different approaches to reference, defining and using reference, and considerations for the approaches they've taken at different scale and in different contexts. So first up, we'll have Barbara Dahl. Barbara is an extension specialist for North Carolina Sea Grant and an extension assistant professor in the Biological and Agricultural Engineering Department at NC State University. She holds a PhD in biological and agricultural engineering and is a licensed professional engineer who joined Sea Grant in 1992 to work on water quality issues. Much of Barbara's current research and outreach focuses on ecological restoration, reducing the impacts of non-point source pollution, and assessing the effectiveness of restoration practices. She's developed and implemented several innovative stream restoration projects, including a multi-million-dollar three-phase project to restore Rocky Branch. Barbara currently serves as the principal investigator for more than $1.2 million in grant funding, which supports outreach and research projects focused on evaluating the performance of stream restoration efforts, developing new techniques for ecological restoration, stormwater management, and assisting communities with water quality and quantity challenges. She manages a team of engineers and graduate students who are funded by these projects. And she's authored numerous publications on stream restoration and stormwater runoff. Then we'll have Art Parola. He's the director of the University of Louisville Stream Institute and a principal at Riverine Solutions. Art specializes in design of stream wetland systems, riverine mechanics, sediment transport, and stream habitat near highway crossings. He's directed the design of more than 52 miles of stream mitigation with hundreds of acres of riparian wetlands. His projects create self-sustaining, diverse aquatic habitats that are highly resilient to floods and accommodate variation in sediment and debris loads. Art has partnered with state and federal agencies on stream restorations for threatened and endangered species and projects requiring complex riverine modeling. He also provides training to contractors and regulatory personnel, has extensive experience with urban restoration and aquatic organism passage, and has designed best management practices for urban outfalls, bridges, culverts, and other infrastructure. Excuse me. And finally, we'll have Alan Herlihy. He's a professor at Oregon State University in the Department of Fisheries and Wildlife. He received his undergraduate degree in chemistry from Northwestern University and an MS and PhD in environmental sciences from the University of Virginia. His research projects focus on developing survey design methodology, assessment approaches, and ecological indicators for assessing surface water ecological condition at large spatial scales. He's currently a senior NRC research fellow working at the Corvallis EPA laboratory, analyzing data from the National Aquatic Resource Surveys. So as you can tell, we have a really amazing panel. We're really excited to have them here, and we're excited to hear their presentations. Before we get to that, I just have a few logistics. All of the participants are on mute now, but we really do hope you engage in the webinar today and ask as many questions as you'd like. As always on these webinars, I do like everyone to get warmed up in that question box. It's on the GoToWebinar control panel on the right-hand side of your screen. So if you could type in there now, how many people are listening to your webinar, to this webinar from your office and where you're located. Thank you for that. Without further ado, I'm going to pass it over to Barbara.
Well, thanks for including me in the webinar. What I'm going to talk about is the reference reach, how it's used as a template for natural channel design, and also how it can be used as a tool to gauge ecological functional uplift. You know, stream restoration is a growing science and practice, and in North America, it's estimated we spend over $1 billion annually. In my state, home state of North Carolina, we spend tens of millions annually, and mitigation projects can run $285 per linear foot. And there's a lot of growing literature that's out there on stream restoration. Natural channel design, just as a review, is a fluvial geomorphology-based method for designing stable natural channels. It was developed by Dave Rosgen. It involves an analog procedure where you take measurements from reference streams, scale those, and apply them in your restoration design. So here's an example of a project he actually did in North Carolina. So the method does rely on these kind of high quality reference streams and from the appropriate hydrophysiographic region in which you're working. And so we have examples here of coastal plain, Piedmont, and mountain streams. So what makes a stream reference quality? It has to be in dynamic equilibrium. This was defined by Leopold, Woolman, Richard Hay later, and Roskin himself. And so in other words, you want a stream that has little to no incision and is well connected to the floodplain. To develop a database for your design, it requires extensive survey of the dimension, the plan form, and the profile. And then all that data is scaled from the reference stream to the design stream by developing dimensionless ratios. So you just divide by area, width, mean depth, or average slope to get that. So here's a long list of all the variables that you have to collect, the metrics you collect from a reference channel, the dimension, plan form, longitudinal profile, and also the substrate as well, because you would want a stream with a similar substrate condition for your reference reach. In 2008, the federal mitigation rule had an update, and it required that we replace function of streams to making sure to include physical, chemical, and biological properties. as well as to develop, evaluate projects based on function-based performance standards. In North Carolina, prior to this update, everything was pretty much on linear feet with some geomorphic uplift, kind of only physical processes were used in the evaluation, and credits really are primarily linked to design rather than the actual outcome or effort. Currently, we're starting to apply some functions, but they're not uniformly applied, but credit is still mostly linked to design effort. So there's some room for growth in that. The functional pyramid was developed by Will Harmon with Stream Mechanics in conjunction with U.S. Fish and Wildlife and EPA and other agencies. And basically, this was a conceptual framework that was developed to guide this kind of functional restoration approach. The pyramid asserts that stream functions are interrelated and build on each other in a specific order. So biology functions are at the top of this pyramid and really therefore supported by all the underlying functions. Because watershed condition or that hydrology, the bottom really influences everything, you're not going to really have good elements in the pyramid without that good foundation as well. So for natural channel design, we are working on these disturbed channels, and we have these reference streams that serve as a model. So in order to gauge whether or not we're having functional uplift, it's important that we collect data from these channels and then use that as a guide to determine if that restored stream, how it is performing. So we have to develop that performance scale. What's the range of conditions that exist out there in the natural environment all the way through all those conditions? So this leads to a lot of the research questions that I've been focusing on for the last 10 to 12 years, kind of looking at what tools are we going to use to evaluate this functional uplift. How do restored streams actually compare to some of the high quality models they're used against, and what factors such as the watershed landscape or even design choices of an engineer actually influence the outcome of that project, its condition and function. And then from all that, what do we learn to actually improve the project or be more innovative to maximize that ecological function? Today for this, I'm going to be focusing on more of these first two elements since this is focused on reference for each channel. So as far as using tools to figure out what tools can help with that, we did a project here at NC State that looked at 5 rapid assessments and applied those to 65 streams throughout North Carolina. We have a mountain region in the west, Piedmont in the center, and coastal plain on the east. So these 5 assessments, the first 2 were developed by NC State, the EGA, and the SPA. The other 3 are developed by Environmental Protection Agency. The RCE was developed by Peterson, and the SVAP was developed by the USDA. The first method, the EGA, is the most involved of the methods. Even though it is a rapid assessment, it requires a full team with knowledge in vegetation, macroinvertebrates, and stream restoration. And it is a quantitative and qualitative method for assessing the stream. Whereas the other 4 can be done by a single individual, they're more of all qualitative metrics that are done. And you will see over here on the right that there's a number of variables that you measure at the sites, and these are the variables of those that we used for our assessment. And with all these assessments, you go out and you take a lot of measurements, and at the end of that process, you either average all those metrics or you sum them and average or some combination thereof. So there's some arbitrary weighting of the importance of each metric through that kind of adding and summing and averaging process. So one of the questions we had is, because we do care about biology of the stream, and that's likely an important outcome of a lot of restoration, is how well do these assessments predict stream biology? So we did sample in all 65 streams, the macroinvertebrates there, and we calculated 6 metrics from those and use those as to see how well these assessments would predict those macroinvertebrate metrics. We did focus in heavily on EPT taxa, that stands for Ephemeroptera, Plecoptera, and Trichoptera, which are species that are very intolerant of poor water quality and habitat disturbance. So they're good indicators of health of a stream. So the hypothesis, well, the literature showed pretty much most of it when people had applied these assessments, they find very poor correlation or prediction of any kind of biology in the channel. Well, our hypothesis was that this prediction was a problem was because of the arbitrary weights to the variables. So we wanted to address that. And also we felt that a lot of them, they do not really assess the watershed condition. And like that pyramid showed, hydrology is the foundation for all of those other pyramid functions. So we felt that we must consider watershed factors as well in the prediction. So we did a GIS assessment on all 65 of the watersheds. We had 6 metrics we measured. The top 4 are very indicative of development conditions, and we saw kind of standard trends across the 65 streams that has developed impervious. These things increased, that we had a decline in the number of these EPT indicator taxa in the stream. Also, if you look on the bottom right there, you see that basin slope is a very strong predictor of EPT taxa, and that's simply because we have more EPT in our western Piedmont Mountain streams of the state. So then we took this manipulation of the data in order to predict EPT. So to address this arbitrary weighting, we did principal component analysis. So instead of just taking that final number, we did this ordination statistics of all variables and did some variable reduction, eliminating things down to about capturing 70% of the variability of our data, and then use that as a predictor. So if you look at the graph, and the blue bar shows the single score. What I have here is the correlation coefficient, or R squared, for predicting EPT taxa in the streams. And the blue bar is the single score. So you see very low correlation coefficients, confirming what others had seen in other studies in other areas. So, but if we look at the orange, that's the resulting principal components. So those variables, for example, EGA had 44 variables. That was boiled down to 11 principal components. But you see we have much higher prediction ability with that, reaching almost 0.7 with the EGA, with the principal component analysis. Then the gray bar adds in the watershed condition, and you see those predictions jump even much higher for that. So, and in fact, if the EGA turns out to be the best predictor, and remember that's the one that is the most detailed and has some quantitative metrics to it. If we look at watershed, this watershed element includes no reducing the variability, all of it's there. Watershed alone happens to be a pretty good predictor of EPT taxa. So that kind of confirming that pyramid framework that we see. So what this means is that these rapid assessments, we're actually asking the right questions. We're going out and measuring, and even if it's a mostly visual qualitative assessment, they are accurate for predicting the biology of the stream. So in fact, these type of assessments are okay. So then we wanted to look at how well restored streams compare to high quality streams and kind of get at that issue of what's the scale of performance for streams. So we used the NC State SPA method, applied that to 156 streams, including restored, impaired, high quality reference streams, and some reference streams that we visited that were good quality, but they had some bit of incision, so they were not really considered what we would use for designs today. So we applied this SPA, and we used all 17 of the metrics in that, and again ran that ordination statistics, kept the first 3 principal components in this graphic here, 3-dimensional graphic, which shows about 57.5% of the variability. So 17 variables boiled down into only 3 principal components. And what we saw is that the reference and restored streams overlay very nicely, which was encouraging. They were quite different from the impaired. whereas the green, the reference and size streams, are kind of bridging across that, kind of showing they have some good and some marginal qualities to those. We also did factor analysis to look at in better interpretation of the data. What does that mean to our stream restoration designs? We came out with 3 kind of factors that were interpretable. The first of that is morphologic condition. It's made up of stream bank condition, floodplain function, stream bank vegetation, sediment transport, and the pattern. And what we see with that is that the reference and restored streams lined up very nicely. There was good overlap, no significant difference in that data. So that meant that in terms of these variables, designers are hitting the mark. They're achieving those kind of really physical morphology elements. With stream habitat factor, that's root mats, overhanging veg, leaf packets, and undercut banks, we saw a different story. Instead, we have a wider range of condition in the restored streams and a lower mean than the reference condition. They're quite different. So what that means is that engineers or designers are maybe hitting the mark on some projects, but other projects aren't making the bar for that. Bed form, which is mostly about riffle and pool position and condition, we found a similar story. Again, a bigger range of data and a lower mean than we have for the reference stream. So more work is needed on the bed form in addition to that those habitat elements. So it kind of gives some good direction on where we need to improve on our stream restoration projects. I want to go back to the pyramid now and talk about some current research that's going to wrap up around the summer that's being done by my master's student, Sarah Donatich, and she's looking more closely at the pyramid and the tools that go along with that. So to accompany the pyramid is a stream quantification tool that Harmon and others have developed. And what this tool includes is that you have to do a rapid condition assessment of your stream. So there's a number of metrics. You go to the site and you assess that. And then you put all this information into a spreadsheet that includes performance variables built within that. So in other words, you put your field measure data in, it outputs some scores, and then you end up where it adds all scores from the 5 pyramid categories, and your outcome is a score between 0 and 1, and there's the ranges on the right to show what score you need for functioning, functioning at risk, and not functioning. So there's kind of 3 categories of condition within the SQT. So built in that spreadsheet are these performance variables where you put your field value in and you output an index value, and that will, by color, you can see what's not functioning, functioning at risk in yellow, and functioning the range in green there. So the SQT contains 28 variables within these kind of 5 classes, and it's not expected that a designer or a project manager would use all these. Rather, you would select out the variables that would be most appropriate to the project that you're doing, or even the budget for which you can do the assessment. It also includes a restoration potential for a watershed catchment assessment. So my master's student, the questions that she's working on specifically related to the SQT is how accurately it can measure or detect restoration success. What is that natural variability range for our Piedmont region for the streams? What do we see there? So we know that scale, kind of getting back to my point earlier. And then which function-based variables correlate best with good biological conditions? So what predictors should be weighted more heavily because they do better predict biological condition. And for this, I'm going to focus on the item number 2 there, that natural variability range for this, since we're talking about reference reaches. So for her project, though, she has gone and applied the SQT to a number of streams around the state, including 18 of these high-quality reference reach streams that we did work on in 2007. So we went back to revisit those. One high-quality biology stream that we wanted to make sure we did have one stream that we knew to have very good biology. And she did a set of 12 streams that were paired, restored, and degraded sites. Today I'm going to focus on these 19 streams here that are more in the reference condition relevant to this. She did assess 21 out of the 28 variables. We had some where we had limitations with our project scope and funding. So we did most of those 28 variables. Again, we want to test them, as many of them as we could. So there were a lot of work, and there's a lot of work and several visits in the field to acquire all that data. So here's some examples of us in the field. We did also sample the macroinvertebrates. That was done by Dave Penrose. He's a former employee of NC State and a benthic ecologist. And here's some of the pictures of the reference reaches. Some of these streams, I said we had been to them in 2007. When we returned, we saw some that had some degradation to them since previous visits. So we had some areas. You'll see some bank erosion there in the lower right. So some of those streams we did not consider any longer kind of the high quality reference stream that they may have once been. So when we look at the SQT results, the final scores are there in the brackets above. This is all 19 of those streams, including that biology reference. And what we see, and each bar shows the color coded by the different levels of the pyramid where the scores vary. And we can see that only 3 of those sites actually scored in the high quality or functioning range for the stream SQT pyramid, whereas the rest of the remaining streams were designated functioning at risk. And if we look at the range, we've got some bar and whisker plots on the right of each of those categories, hydrologic, hydraulic, etc. We can see the range of scores for those parameters, and we see we have a lot of range in hydraulic and the biology for these 19 streams. However, if you look over here on the left at this gray bar, that's the final output score from the SQT tool. So the variability is really dampened by that averaging of scores. And it's worth noting that for those categories such as geomorphic that have a whole lot of variables in those, each variable then becomes very kind of watered down in that process of adding and averaging of the variables. So a category like hydrologic that has fewer variables is going to have more weight in that final SQT score. So also I just want to quickly show you some of those, our analysis of the performance ranges that are built into the spreadsheet. Again, here's an example. This is the soil compaction one that's really determined by the instrument, a soil penetrometer, for doing the assessment. So you put your field value, you measure with the penetrometer here in the X, and then we'll output the functional index score. And up here at the top, we have the ranges of those scores of the index for functioning, functioning at risk, and not functioning. Then on the right, I show the scores for the 19 reference streams that we have. And if you look, you can see that most of the sites actually fall in that functioning at risk category. Only a few of those are functioning. So this may indicate that built into that spreadsheet that the range it's selected may not really capture, may need to extend the functioning range. Because even though some creeks have some erosion, they overall are pretty high quality for the soil compaction. Similarly, here's the pool-to-pool spacing. So this has a kind of double edge range where if you're too low on pool-to-pool spacing or too high for pool-to-pool, this is isolated to meandering C and E stream types with riffles and pools. We have an outer range for both on not functioning. And then at the top, you can see the ranges of scores for the metric for functioning at risk and functioning. So on the right, again, is our box and whisker plot of our 17 of the C and E streams. And then what we see here is that only a section of them fall on that functioning category for pool-to-pool spacing. So again, this may be that window of functioning may need to be expanded a little bit. I just want to point out a lot of the performance variables were based on literature and some professional kind of experience from Will and Harmon and others, the team that was working on that. So there may need to be some refinement of these variables based on region. Just a quick note, I want to share a little bit about the biology. Here we have the biotic index score, which kind of moves, is a smaller number as you have a higher quality stream, so its value goes down. And we see also the EPT taxa richness increasing, so that's to be expected, that relationship where we have excellent water quality, we have a lot of EPT taxa. We also have on here the percent shredders. This is a metric that's in the SQT that is used as an indicator or proxy of organic carbon. But we saw kind of an odd range with that. If we look at the poor condition streams, we see that's dominated by there was a high score for percent shredders, but that's dominated by amphipods, immature crayfish, and isopods. However, when we move to the kind of middle range streams, those were dominated by chironomids for those. And then the high quality streams are dominated by actually more of the EPT taxa types, stoneflies, mayflies, and caddisflies. So this kind of suggests that there may need to be some more specific shredder species that are included in that metric for evaluating this as a proxy for organic carbon. So with my student, Sarah's research, Sarah Donatich, the next steps for her are going to be evaluating some of the statistical relationships between landscape, design, and these benthic variables. So kind of taking out those elements of the pyramid and see which of those metrics best predict the biological composition of the stream. And so that we can relook at the significant weights that are built into that tool to get those final scores and make some recommendations on what variables need to be shifted to more weight because they are a better supporting of good biological composition in this kind of Piedmont physiographic region. And if we have time, I'm happy to, I want to acknowledge a lot of people did participate in this, and if we have time, I can answer some questions.
Excellent. Thank you so much, Barbara. If anyone has any questions, please feel free to type those in now, or we'll switch over to Art as we go. That was a lot of really great information. Thank you, Barbara. Really, really interesting. I'm not seeing anyone typing in anything yet, so I'll move over to Art, and if you do have any questions for Barbara, we can ask those at the end. So thanks again, Barbara.
You're welcome.
Okay.
Am I on?
You are on.
Great.
There we are.
Thank you.
Perfect. Thank you.
Thanks. So I'm going to talk about, I'm going to focus basically on eastern U.S. streams, and their riverine wetlands are usually associated with those. And for first order to fourth order streams, mainly in my talk here today. So if you think that maybe this doesn't fit, it just maybe think about those issues or that restriction. The other one is on a larger side of the scale is the I would say the size of a stream that a beaver would no longer block would be the upper range of what I'm going to be talking about. And as far as that ecological reference goes, Barbara talked a lot about using the least impacted streams, or the reference streams that are the best of today's streams. And I'm going to present something here that tries to go a bit beyond that, streams that we maybe don't really see today, but try to imagine the functions that were there and then trying to match those functions and values of those kind of streams from a historical standpoint, and think of maybe not necessarily being limited to this kind of streams that exist in the best quality today in certain ranges of watershed sizes, certainly because of the human impacts. So that's what I'm going to focus on. And before I kind of go through all that, I'd like to acknowledge several organizations that have contributed to this work, and especially those that have kind of allowed us to go beyond the standard techniques that are available to try some of these different things out. I'm not going to go through all of them, but there's a list there and you can take a look at them. The other one are the contractors that we've worked with, especially these two groups that have contributed significantly to our work and how we do things, because they're the ones who are actually moving soil around and digging out there. So when they find things, they bring it to our attention, and we kind of work through things to improve them as best we can. And given that these are generally not standard techniques that we're using, that they're really helpful in that regard. So first, Barbara talked about using ecological references to essentially assess the effects of a site to what its condition is today, and then the lift you might get when you change from the conditions and functions that it has today to the restored condition. So that's really what this first part is about: is what conditions and functions do we have that have been degraded in the system, and what were they like maybe historically. And again, I wanted to try to look at historical conditions, because that probably is the upper end of the functions that have been lost, right? We had some kind of historic condition, we have human impacts, and the difference between those is what's been lost. So that assessment is using these ecological references, kind of a scale, is important for that. From a design perspective, what objectives should be put into a design to restore the functions that have been lost? Again, there, if we shoot for a condition that is affected, then maybe we didn't hit a target as high as we could have. So we want to look to something that is maybe, again, might not exist today, to try to look at the functions that have been lost, and that we might be able to set objectives in our restoration design to kind of meet those higher level ecological functions. The other thing is about the stability, robustness, and sustainability. When we're looking at those kind of things, when we first finish a project, it may have all kind of nice habitat in it, but how will that habitat be maintained over the long term? Again, those are something we need to think about when we're, as designers, and looking to historical information might lead us to something that is perhaps sustainable in the long term. The next thing is, once we've constructed a project, what's the difference, the lift that we would get that Barbara talked about between these functions that we would want to replace and some reference that may have existed in the past, and what functions we want to put back into that system. So how much of those functions have we replaced, and then to what degree have those functions been replaced? With the historical perspective that I'd like to take on this, there are certainly constraints in these systems that would affect whether you could get back the full functionality of a historic system. We all realize that we're not trying to exactly necessarily match what existed in the past, but again, get those functions like groundwater connectivity, mobility of sediment, the plant communities that might have existed in these environments in the past. Barbara did a great job of talking about the least disturbed or the best reference sites that we have today. And this site here is actually a section of old growth forest that exists in Kentucky. And it's extremely valuable to go there and to look at how the streams are moving through that system, how they're interacting with the vegetation around it. But the problem is that there are relatively few of these that haven't been significantly impacted. And as a consequence of that, of having so few, we sometimes can get a target that isn't as high a target as we might be able to obtain. The other thing is, these systems that are very, very least disturbed and haven't going through some kind of recovery process, there are very few of those, and the ones that we do have tend to be limited to somewhat atypical conditions, where people couldn't get to the site somehow, or there's some kind of very steep gradient. There's something usually very unusual about the site that makes it kind of quite a bit different than if we had the typical situations that we're faced with. Kentucky has done an interesting, or very good job of trying to piece together what the history of the state was from the time when Native Americans had quite a bit of agriculture in the western part of the state and did burning through most of the state for for hunting purposes or for agriculture. And a lot of Kentucky was actually savanna-like or prairie-like. And so understanding that those conditions existed with beaver included to it can give us some perspective on what existed before people impacted the state. Sometimes we like to use these historical maps that show streams probably during some period during settlement. Usually when people were being taxed, they would develop maps of some sort. So you get some idea of what the streams were like then. And the comments for a lot of Kentucky streams were that they were very crooked. But the issue there is that by the time they developed the maps, the beaver had already been removed from pretty much all of the state. So what you see is probably streams that were, even as they're tortuously meandering or crooked in the state, were not pristine at all. So we really don't have any good maps of streams before settlement. But what more and more evidence is coming out is that streams were dominated in this range of from probably large watershed first order streams, larger watershed first order streams to fourth order streams by beaver. And that the beaver dams may have gone all the way across the valley and given us a series of dams like you see in this picture here, with streams in between, varying in lengths from over large, depending on the area, the slope, and some other variables. The difference between dams may have been several thousand feet to maybe not at all, maybe just beaver dam after beaver dam. And if you can imagine, before maps were really made of anything, these systems being, again, we don't really know to what extent this kind of situation was, but it probably was, based on where we see beaver today and some of the evidence that we find when we dig through these valleys, they're probably over a good portion of the streams, again, in that first to third order size. So, but over most of the area, we don't have this kind of data from what things were like with the beaver before settlement. So where could we go to get some of that information? And where we go most of the time is in this, to look at the valley stratigraphy and try to piece together at least the materials that are in the valley bottom. And a lot of times that gives us an understanding of what was there before, and it also may give us an understanding, and usually does give us an understanding of what could be in that valley bottom. On the right, you see the typical picture of a Atlantic coastal area, Piedmont stream, and where you have some gravel over a degraded bedrock on the bottom, where you see that red color in the very bottom of the picture on the right, and above it is soil that probably persisted for thousands of years, just above the gravel, and then above that, material that came in after settlement. And so we have this mass of very fine material that's over top of gravel underneath. On the left side, we have a picture of a stream bank cutting across a valley where there's gravel and cobble mixed in. The interesting thing is this gravel and cobble in this stream right here is not a whole lot different than the gravel and cobble that's underneath this stream. So the size of the material is very similar, but the actual stratigraphy of the valley bottom is completely different. The valley widths on both these streams aren't that different. Both of them are about 100 feet wide or so, and the gradient on the valley isn't all that different. So if we didn't bother to kind of think about what was underneath this valley, we might think that the valley type is the same. Why can't the stream system be similar to each other? And if the materials are the same that might be in that stream. But the problem is that the groundwater system in each of these systems is quite different. And how the groundwater system would interact with the stream is quite different. So trying to piece together some model of what may have been in these streams before, I would say in these two cases, is extremely important. This is another case where we dug across a valley in the Allegheny Plateau in southeast Kentucky. And you can see this brown soil. Typically you see that in most of the eastern U.S. where you have this brown soil over top of some buried soil. And when you dig down far enough, you get material that looks like this chewed up wood material. And it's just over top of the gravel. And dating on this looks, I believe it was about 1,000 years old, or 81,000 for the dates on some of the carbon that was taken out of the wood. And the depth over the bedrock of that wood was no more than 1.5 feet. And the other 10 feet over top of it was that fine material where you could not find a piece of wood in it. So we see that at least here, there's some good evidence that the beaver had dominated this valley. This is another site where we're looking at, again, the profile through the material, where at the top there's a layer of a relatively new soil, and we have a buried soil about 2 feet down from the top. And in the very bottom of the pit, we have the groundwater level. And here, the stream was perched over on bedrock on the hillside and completely separated from the gravel in the middle of the valley. In fact, the stream dried up in the summertime, yet the middle of the valley had gravel in the groundwater. So understanding that groundwater system and the stream is really important to how that stream will function. This stump here was found in the Kentucky River floodplain. It's a stream that was relocated and kind of removed all the material. And this is where we find these large trees or evidence of large trees. It's on big river floodplains. We really haven't run into a case where we found a buried large tree in these first to fourth order systems when we've dug across these valleys. And I've asked several people about that. And the reason that's important, I think, is that if the beaver dominated these systems for the first and to fourth order, then there probably wasn't a hardwood, a large mature forest at that location. And in these cases here, where on these bigger rivers, there is evidence of large trees in those systems. So based on these digging across the valley and other people's work like Dorothy Merritt's and Bob Walter, of Franklin and Marshall, and others around the country who have done work on this, there's a picture that could be put together of what these historic streams were like and what their functions may have been, and probably were. One thing we know is these systems were generally very retentive of carbon and sediment that did get through, and there wasn't perhaps a lot of sediment getting into these systems. So they're retentive of carbon and not much sediment. There's generally a thin layer of material over the bedrock, at least in much of the eastern United States that's not coastal. Coastal environments were quite different, but the non-coastal areas generally had this configuration with bedrock, gravel, and then a little bit of soil on top of that. The streams were not necessarily single thread, but multi-thread. And there was a wetland complex that was adjacent with it, where the groundwater was interacting with that material underneath the channel, and the root systems of trees and vegetation were generally in that zone where the groundwater was, at not a very large height. So banks were very low, floodplain connectivity very high, not necessarily a floodplain, but some kind of interacting surface that was kind of integrated into the channels. Channel connectivity with groundwater was direct. The gravel, the groundwater were very close to one another, and tree roots had access to this groundwater, or just above the groundwater. And the stress was low, not just because there was low amounts of, because the discharge from the watershed, which was forced, it may have been low, but at the same time, when you have bank heights this low and the stream is able to spread across the floodplain at such a low level, much more frequently than 1.5 year, 1 year event, maybe probably multiple times a year, maybe 30 times a year, it would go across that floodplain, then the stresses are extremely low because it's spread out over that entire area. You flip to what we have today, where these areas are buried, and we end up with that gravel layer being buried by several feet of silty, sandy material. And that changes everything, because now we have streams that are incised with high banks. Those high banks allows the streams to be contained. The containment causes stresses to get very high. As stresses go up, the mobility of the sediment goes up, the bank erosion occurs, freezing and thawing on exposed large banks. All of that stuff kind of kicks in. And that's, everybody kind of, I think, agrees to that issue. The streams, though, have cut down a lot of places right through the gravels. And sometimes the streams are even into the rock below the gravel. And so those groundwater systems are completely different now. Now we have the trees sitting up on those soils and maybe not interacting with the flow at all. And we have the trees outside of those gravel layers perched high up. In some cases, if you look on the right-hand side of the picture, the streams may even be perched on the silty material that's underneath. You saw that one shot where I showed that tributary to the Kentucky River, and that stump, the stream was kind of above where the stump was. This would also apply to some of those rivers that are perched up on, that have those same kind of sediments perched like that. So we have high banks, floodplain connectivity is significantly reduced. The channel connectivity to groundwater is completely different than it was before. And the interaction with the floodplain is different with that connectivity to the groundwater. The tree root access to the groundwater is significantly changed. And the frequently a substrate movement is completely altered as well. So all of these things, what's going on here in this picture, not just the floodplain connectivity, most people strive for that floodplain connectivity, but all of these other issues as well have changed. This is another example that we run into a lot in the in the Allegheny Plateaus, where we have, again, bedrock with a thin layer of material over top that's composed mostly of gravel, but not always completely gravel over top of the bedrock. We have this buried soil layer that's in here, and then we have some material on top that came in and maybe was even pushed around and reworked many times for many reasons, maybe logging, farming, whatever, the many reasons why people would have moved material around on top. The thing is that this stream here has cut down into this rock. This is one of the biggest, most important aspects of this problem is it cuts down to the rock and it cuts through that gravel layer that's in the bottom. And then when we have flow, even in the springtime, this water is going through that gravel and being drained by the channel. And we believe historically that stream was up on top, and there's some evidence for that the streams are up on top of that gravel, and then at least in the springtime, that water was at least filling that gravel layer up. The issue here is that if it doesn't look like that's a lot, it's only a foot, but if you multiply that foot of groundwater storage while there's water available in the springtime, if you multiply that 1 foot times thousands of miles of stream that are in this condition, you end up with a lot of water storage that's lost in the springtime. And then in the summertime, as that water would be released from that groundwater aquifer back to the dry periods when it would be released back to that stream, you don't have it because it was already drained in the springtime. We have found in some places where we've done this, that where we put the stream back up, kind of in the position where I've shown here where we think it was historically, that streams have gone from intermittent to nearly perennial, at least in terms of water being available in the stream. I just want to talk quickly about this stream evolution model that was developed by Kluwer and Thorne, that is relatively new, just about, well, it's almost 6 years now. But the point is that the streams, they now believe that streams in their original form were more branched, and the groundwater was higher and mixed in these kinds of anastomo, excuse me, anastomo. I always say in a branch, so I'm just going to say in a branch for these. Sorry about that. So the interbranch systems that are either wooded or kind of emergent, kind of wetland type systems, and that when you disturb these kind of systems, they tend to turn into these other things that we observe today, where the streams are down cutting and incising and all the other kind of evolution models that everyone has always talked about for maybe 40 years now. But the big change is that these kinds of systems have a very high benefit from an ecological standpoint. And I'll show an overlay of this picture in just a second, of this diagram in a second, that will illustrate the point. Most of the systems I would think that we're shooting for today in terms of the restoration that are not multi-thread kind of wetland systems like these on the top here are arrested and degraded systems that are somehow arrested by bedrock, large material, culverts, some kind of controls that get in place and stop them from changing a whole lot. So we end up with these kinds of systems are probably the ones that we are obtaining our reference conditions from. And we'll see later that those are not the optimal, or nor do they represent the historic conditions and the benefits that we had with those historic systems. So what Kluwer and Thorne did is they looked at the benefits of each different kind of channel in this evolutionary model. And when you do that and you overlay them, you're going to see that these benefits of the multi-thread channels in these wetlands are much more significant than the arrested ones, or even these other single thread stages, if you will, of change are. I'm sorry. The benefits of those two conditions are the multi-thread channels is much higher than the benefits of the other systems that we typically think of as targets for restoration. The only thing about that model is it doesn't include beaver, and it's interesting because if they were so dominant, and I think many people believe they were dominant before, that these still have not really been incorporated to a high degree into these kind of evolution models. The other thing is these systems that have beaver in them, it might take 10 years or 20 years to get them to recover to something like this. But if you think about the other kinds of reference conditions that we're generally shooting for, that is to like have a mature forested floodplain adjacent to a channel, that mature forested floodplain could take at least decades to mature and get to a point where we would say that that's kind of a final state. Whereas these beaver complexes, you probably get beaver complexes. This one, for example, here is back in less than 10 years. So, can we achieve these functions of these things? I think it's very doable, and it's being done, that you can get these kind of systems back in a relatively short period of time. The question are the constraints of these systems. What's in place that constrains our ability to get these kind of systems back? So I just want to leave with end with a couple of thoughts here. One is consider the regional historic information for the stream and valley characteristics of the impacts. There's a good chance that we can put these streams back the way they were before, or at least function similar to the way they were before. And using that valley stratigraphy to inform that ecological reference is extremely important. And consider the effect of the loss of the beaver. I don't think we should allow the current least disturbed reference sites to limit what can be done. And from a regulatory standpoint, or from a even the way we're biologically thinking about references and what kind of maybe bug community existed or fish community existed, these we might want to be thinking more about what may have existed and try to hit a target that is beyond what is available today as our least impacted sites. I think I'm just going to let the rest go here for you to read. I think I've gone a bit over time, so I'll stop at this point and take questions or let it go on.
Excellent. Thank you so much, Art. That was really interesting, and we definitely appreciate your discussing this approach to reference. We did have one question come in, and I'm going to ask that, but I will change over to Alan after that so that we can get through that, and then we'll have a little bit of time at the end. So there was one question about when you were discussing the changes over time. Do you understand where all the new soil is coming from that's sort of changed conditions in those systems?
Yeah, well, a lot of people think that has come from either the logging or farming practices from the upland areas.
Okay,
could be
great.
real big. Anything that would disturb the soil. There's also the effect of channel straightening, where streams have during the when people did farm these fields, they straightened the channels out. They did all kind of manipulations, and as that happened, the head cuts were generated, or degradation waves that were generated when they manipulated those channels. And even when they took the beaver dams out, the beaver dams provided control across these valleys. When they took the dams out, there's good evidence that the streams degraded almost immediately. And when those streams degraded and they got to the hillsides, the degradational waves probably went up even into to make gullies upstream of each of the tributaries that confluenced it with it. And then when farming communities got in, people went in and farmed, they certainly manipulated and managed the water just to drain the valley, to relocate the streams, to get them out of the way, and to drainage for crops so they didn't flood. And all of these things propagated up into the headwaters and created large sediment loads downstream. Dams were certainly a big part of that as well, in terms of creating backwaters so that to catch this sediment.
Excellent. Yeah, thank you for that. I really appreciate it. So we're going to move on to Alan. Just a reminder, please definitely type in those questions that you have for any of the panelists as we go forward. Thanks again, Art and Alan.
Great. Thanks, Rebecca. Is the audio working well?
Yep, you sound great.
Good, good. I always have this fear I just launch into this when I'm on mute.
Right.
10 minutes before anyone finds out. What I'd like to talk about is kind of what we've been doing for reference sites for making the kind of large-scale national assessments that EPA has been doing over the last 20 years or so. And I didn't put together an acknowledgement slide because there's just so many people have been involved with this work that it would have just taken too long. So I'm kind of standing on the shoulders of giants with a lot of this. And before I launched in, I've found over time that reference seems like a fairly simple concept, but it really does mean different things to different people. And it really does, I think, largely driven by what the objective of what you're trying to do. So to be specific for what I'm going to present in this webinar is that we're kind of looking at defining and the use of reference sites for, how do we deal with a whole national scale set of biological data to kind of report on it for, is the biology in good condition or poor condition? And so a major challenge when you're kind of conducting these kind of large scale assessments is, determining what is the appropriate standard for comparison. And didn't want to get into EPA alphabet soup here, but a lot of my slides will have these various acronyms for these. Started doing these kind of large scale surveys back in the days when it was kind of a research project run by the research office. It was called EMAP. And it's now kind of in, I call production mode. The Office of Water is now running, annual national surveys for different aquatic resources. And the key piece of these is that there's a large set of randomly selected sites so that you can actually infer the condition that you measure to the whole country. And then we also handpick a bunch of additional sites that we are hoping to be potential reference sites. And when we do our biological assessments, we're doing a reference condition approach. And right now we're doing kind of national scale rivers and stream assessments, the national lake assessment, the national wetland condition assessment, and the near coastal condition assessment. But I'm going to focus on streams for this webinar. And we need reference sites to do our biotic index development when we're trying to come up with some kind of overall biotic index to report on, what's the condition of the biology. So we need reference sites to develop, the scoring and the selection, modeling of these metrics. We also use the population of reference sites to define what is good, fair, and poor. And in addition to the biology, we've also kind of adapted this approach to do the same kind of things for just nutrients and all sorts of the stream habitat condition. And there's also been a big predictive modeling effort, which I won't go into, but essentially you use reference sites to model the expected taxa list, and then you just compare it to the taxa that you found at the site. And all of these approaches need a whole population of reference sites because we're doing a lot of statistical analyses. Just real quickly, how we kind of use these reference sites. One, when we're, literally develop hundreds of community metrics for fish and macroinvertebrates. And we have our least disturbed, what we'll call our reference sites, and we've also developed a list of most disturbed sites. And you're trying to find metrics that, tell them apart, as opposed if you have a metric that doesn't tell them apart, that's probably not one you want to use in your index. The other way we use them is that once we have our population of reference sites, we define this kind of good and poor based on the univariate percentiles of that set of reference sites for the specific class that you're looking at. And what we've done is we kind of say if we have a biotic index score here, generally we go from 0 to 100, and with high being good, you would say, well, if you're below the 5th percentile of this reference population, we're pretty sure that you're not in good condition, and we're going to call that poor. And then we've used the 25th percentile, the reference distribution, and above to be good, and the area in between is fair or marginal. So how are reference sites picked? Generally, in a lot of surveys that I've seen, it's kind of a compilation of best professional judgment lists of sites. People will say, well, send me your good sites and we'll put together a list and we'll go sample, 50 of them. In my experience with doing this in various surveys over the years, it's not had a high success rate with that. Often the failure rate is about 50% of you get these hand-picked sites, and when you actually do some objective screening of them, half of them really turn out not to be referenced. I really don't have a good answer as to why. It's been repeatable over a lot of different compilations and people and methods. My guess is that there's just people have widely varying perspectives and objectives, and when you start pulling large-scale things together, it's a high failure rate. And just this pre-screening in the office helps some, but not as much as I thought it would. Some background, just as the first time that I had to do this was with an EMAP survey in the Mid-Atlantic Highlands. And we, had about 500 randomly selected sites. And we also had about 60 to 70 hand-picked sites that were supposed to be referenced. And when we started having to analyze the data, it looked like the graph here on the right. This white line is the random population. And I'm looking at a cumulative distribution function of, here I'm using EPT richness, and Barbara did a nice job of setting up what that is, so I won't go into that again, but that's just our measure of biological condition. And you can see these hand-picked BPJ set of reference sites are better than the population at random, but they're really not a lot better. And knowing something about EPT with our protocol, things less than 10 were probably not in very good condition, and you really want to see things over 15 to 20 to be talking about good. So if you look at that, we're seeing about a quarter, 25% of our hand-picked sites are really not very good, and we're really not having a lot of good ones. But when we start thinking about, so what are we going to do? We need a population of reference sites to do our analyses. And well, there's really an awful lot of good ones that you just find at random. So we decided to come up with a set of objective filter criteria to say, this is how we're going to define reference site. And we'll screen all 600 or so of these sites that we have, and the ones that pass the screens we'll consider reference. And in this case, in the Mid-Atlantic Highlands, we picked 5 things that we happen to measure. That's actually 6 here. One, we use sulfate as kind of a measure of mining pollution. Generally, if there's acid mine drainage around, the sulfate concentrations go up a lot. We wanted to get rid of acid rain sites, so we got rid of ones with low A and C. Sites with nutrient pollution, we got rid of using total phosphorus or total N concentrations. We found chloride is an excellent tracer of human kind of just footprint. And so things that were above kind of at the deposition level concentrations of chloride, we got rid of. And then lastly, we used one of these rapid physical habitat surveys that we did at the site, and said, if it didn't get up into the good range of this RBP score, we tossed it as a reference site. People ask where these numbers come from. So real quickly, something like here's an example of a mine drainage stream. It's got 5,000 microequivalent sulfate. If you look here in the Appalachian Plateau in green here, at a frequency histogram of sulfate, the mining guys all are out in here when we looked at their maps and the field data. And so basically these are where sulfate's coming from deposition. So we had a cutoff of 400 or more, saying that's our reference filter. You can't just go by looks. This is a stream was up there kind of in one of those state game lands up in Pennsylvania, a couple of mile hike in, a beautiful looking site, but it does have an acid rain problem. It's got a negative ANC, and probably not one that we would want to use as a reference site because it does impair the biota. Nutrient concentrations aren't as kind of with this easy to find cutoff, but we were looking at, if you look at total nitrogen versus say percent agriculture, you can look down here and come up with, we use 750 as our cutoff as kind of what you expect to see in undisturbed agricultural places. So the bottom line is after we did that filter and got rid of all the sites that failed the filters, and we were left with about 100 sites that passed these things here in red, and this is what we use as our reference population. And you can see we had much fewer sites here in poor condition. But what I liked most about this is that we now have a much more rigorous definition of reference other than some kind of BPJ judgment. If we're going to leave something for posterity or 50 to 100 years from now, someone sees this survey data, wants to know what did you use for reference, we have a much better way of communicating this is what we define as a reference site. May not be perfect, but at least it's something you can reproduce. So how did we go about doing this when we had to go to the whole country national scale? And I'll emphasize this was primarily done for a biological assessment. You do need to have some kind of classification system. You can't use the same criteria everywhere. In the Mid-Atlantic Highlands, we could get away with one set of criteria, but you can't do the Great Plains and the coastal plain with the same set of criteria. So basically, we had to come up with, what screening variables do we want to use? I put here in red, we don't use any biological information in defining reference to avoid circularity. Otherwise, you're coming up with a self-fulfilling prophecy about what you think biological reference is. And then you have to set the thresholds for each of your filters. When we were thinking about this, we adopted this definition of reference condition for our sites from a Stoddard et al. Paper. These are basically, in a lot of places, you can't find undisturbed. I would argue there are no pristine sites anywhere in the world anymore. Atmospheric deposition of pollutants is everywhere. So we adopted this least disturbed definition of reference. These are the sites with the best available physical, chemical, and biological condition given the current status of the landscape as defined by a set of explicit criteria to which all reference sites must adhere. So what we did is that we used the same set of filters, the screening variables in all ecoregions, but we set different thresholds in different ecoregions in order to get enough sites to do an analysis of what least disturbed is. In some ecoregions, it's easy to find minimally disturbed sites. In others, you kind of have to relax your thresholds a bit to get enough sites, and that's kind of the least disturbed region. And this does vary among ecoregions. For our framework, we used the Almernick Level 3 ecoregions as a starting point, and then looked at aggregating them into a number that we could actually do with the logistics we had to do a national assessment. And we came up with 9 ecoregions. These are aggregate ecoregions across the country. A coastal plain, and then we divided the Appalachians into northern and southern Appalachians. We have an upper Midwest region, temperate plains. The Great Plains are divided into north and south, and then the West is divided into the Western Mountains and the Xeric West. These aggregations were driven by a macroinvertebrate data analysis we did with a kind of a giant national macroinvertebrate data set I put together across the country for a STAR grant back then. And we analyzed that to look at, where do things kind of fall out? And it came out pretty nicely in that, you got things like, this is the West out here, and these are the Western Mountains are the dots, and the Xeric West are the squares. The Appalachians are here in black, came out, and the coastal plain ecoregions are here. And so it came out pretty well, and we've actually adopted this in the lakes and to a large degree with wetlands. This same kind of scheme has worked pretty well across the country and across resources. I'm not going to go over all the screening thresholds for all 9 ecoregions, but here's an example of kind of 2 extremes. The variables we picked to do screening on, we use total phosphorus and total nitrogen, sulfate, chloride, and ANC and DOC together to get rid of inorganic acidic sites. We don't want to get rid of sites that are just naturally organically acidic. We use turbidity and then 2 habitat measures, percent fine sediment and the riparian disturbance index based on field visits. And you can see how different these criteria can be between things like the Southern Appalachians and the Southern Plains. Quickly, we've had a lot of debate internally about using field data for screens versus using more just office-based, GIS landscape data screens. And we've opted more to go with the field data. I kind of like that because it what you see in the stream is what's actually getting through the landscape and getting in the stream and impacting the biota. Like a GIS measure, say percent agriculture, does matter where the agriculture is and is it being done with best management practices or not. Also, try to get away from just defining like percent agriculture as bad. It's really we don't want the nutrients and the sediment in the stream. That's what's bad. However, there are some things these screens do miss, and so we have adapted just looking at a 1 kilometer circular landscape screen to just get rid of anything that we really gross disturbance that we have missed. So just some concluding thoughts from this exercise. I think it's important to have, for defining reference, have some explicit objectives and the criteria of what you mean by reference. I would say for these biological assessments, it's entirely driven by, the quality of your reference sites. Garbage in, garbage out. If you don't have a good definition of reference, it doesn't matter how fancy your statistics are. And this does require a balance of kind of strictness of what you mean by reference with your desire to have streams spread out across the region of interest, because disturbance is not independent of stream size and ecoregion and types. If you're very, very strict, all your reference sites will be up in the alpine areas of the mountains, and you won't have anything down, in the plains where people are living. And then lastly, my personal opinion is I kind of like the field data as opposed to GIS data when you have it. And with that, I'll be glad to answer questions. And much of what I've discussed here is in the first paper there for streams, and similar approach that we've just finished up for wetlands should be coming out any day now as part of a special issue of the National Wetland Condition Assessment.
Great. Thank you so much, Alan. That was really informative and I think a really complimentary presentation to the other two with, a different way for defining reference. So folks, if you want to submit some questions, please do for any of the presenters. I do have one going back to Art's presentation now, but please go ahead and type your questions in now if you have some. Art, this one is for you. One of the participants asked if some of the photos you shared were restored sites following the design methods that you presented on.
Can you hear me?
Yep. Okay.
Yeah, I'm sorry. I've never done a webinar before, and it felt like I was in the shower talking to myself the whole time.
Right.
So apologize for that. But anyway, yeah, there's several photographs in there where sites that we've done and are monitored, and we have data for actually to show that shows actually that the diversity of species, the biomass of macroinvertebrates as well as fish have increased in these areas quite significantly. So we have data for that. Also, some of them they're putting the threatened and endangered species came back where initially they thought, like the black-side dace that exists in southeast Kentucky and it's on I think the threatened species list. They thought that it needed really dark, cold water, and when we put the wetland system back in there, almost the next year we found dace spawning in those areas that were they're vegetated, but we're still open. And so it's kind of like the salmon thing where they thought that these species needed cold, canopy covered, dense forest areas to be great habitat, whereas that wasn't the case. And now we even have a species of greatest concern type mussel moving up into a 2 square mile watershed that used to dry up every summer. We also have that coming back, and they're using it as a refuge for places where they need to move those mussels to. So seems to be working, and we're able to. It's not just pie in the sky that we're shooting for this pre-settlement condition. And people at Big Springs have done similar things in Pennsylvania that are monitoring it. So yeah, these things are being built.
Excellent. I have a question for any of the panelists. I just sort of was wondering about how any of your work is translating, and I think Art, you've talked some about this, but to compensatory mitigation implementation, either at the guidance or policy development or agency decision making or projects on the ground. Anyone wants to take a stab at that?
So the work we're doing on the SQT is being funded by our in lieu fee program, the Division of Mitigation Services here, because they're considering adopting this, but had wanted to kind of test it out, and also they did have some concern about the performance metrics built in. So our work is when it wraps up will be hopefully influence how, in what form they adopt the SQT for doing functional uplift assessment of restored streams.
And our work is mostly funded through some type of mitigation, so it's actually being used for mitigation purposes of streams and wetlands.
And Alan, are there any restoration sites that are being evaluated as part of the condition assessments or mitigation sites, or is that something states are looking into?
Yeah, I mean, nothing specific. I mean, if a restoration site got hit at random, it would be, they're considered part of the population, if they're on the NHD frame. But we're not sitting there, going through an exercise of, it would be an interesting one, but it would kind of be a separate effort, kind of say, take a random sample of restored sites and seeing how well they match up with what we're defining as reference.
Right, right.
I think an interesting part of this is always, what scale do you want to operate? Because, everything gets local. And so if you really want things to be exactly the way they were at the local scale, you probably need very localized reference sites. If you're trying to do a national assessment, you're looking at a more generalized definition of reference.
Right. I just got a really long question in, and let me see if I can get to the gist of it. Well, let me read it. Art, this is for you. I've heard multiple talks about stage 0 and beaver analog approaches to restoration, and a consistent message seems to be the multi-thread channels are natural historic condition. The channel evolution scenario at Kluwer and Thorne is typically presented as supporting evidence, but the commenter is not convinced of this evidence. They live in northeastern Minnesota, and there are many areas that are remote, including the Boundary Waters Canoe area. With the exception of beaver meadow areas with extremely flat slopes, which are essentially transition zones between wetland and streams, or areas of high sediment loads that are low slope beneath a steeper reach. So I guess maybe the question is, can you comment on maybe how the approach might vary across the country in different kinds of systems?
Yeah, I think that's a good point, that things do vary depending on where you are, the geology, the slope of the valleys. All of those things are certainly part of what affecting these streams for sure. But I guess the removal of the beaver in the beginning, and I'm certainly in Minnesota and Michigan, there are probably systems that look like the ones I put up in front of the screen there. But it would basically, if you put a beaver dam and you've got backwater and then you've got another beaver dam upstream of it, it's likely that the stream that into between the beaver dam might be multi-thread. And there's no reason necessarily for it to be single thread, although there could be a single thread stream there. I mean, I think there's multiple ways that streams can exist based on their history and the way that obstructions and beaver and trees and things grow. I think that's the key thing, is that historically the streams may have not been driven by sediment dynamics as much as what I call organic dynamics. Trees falling, and again, they have to be in the right size range. I'm not talking about the Mississippi River, although the Mississippi River is branched above the Ohio, where it confluences with the Ohio. There's all kind of branching channels in the Mississippi River with islands all over the place. So I think there was more branching than we see today because people cleared the wood out, people cleared the beaver out, and they made channels in a lot of places. And I don't know if the boundary waters haven't been disturbed, but I think they might have been.
Interesting. Well, thanks for that. I think we're at the end of our time. And I really just want to thank the panelists again for some really interesting and really informative presentations. They were great. Appreciate that. And I appreciate all of the participants for being here. Again, we have some webinars coming up. The next one is in April and then 2 in May. We'll be sending invitations for those soon. And please, I would appreciate any comments you have on the evaluation question that will pop up for you after you close out the webinar. It will really help us with our wrap-up webinar. We want to make that as beneficial to our audience as possible. So any input you have would be really valuable. So thank you again for joining us today, and we hope to see you next month for our next webinar. Thanks, panelists. Have a great day.
Bye.
Okay, bye-bye.
Thanks.